that is?
Looks like my sister.
Interesting. Bit of a Rorschach test. Presumably, yeah, looks like it, yeah. Sure, yeah, there's a box over there. Next to the highlighters. All right, let's draw a Lewis structure for methane. Can we do that? Okay. So let's do that. Let's count electrons. How many electrons does a hydrogen give you? One. And we have 4 of them, so that gives us how many electrons? 4. Awesome. And carbon gives you how many electrons? 4. So we have a total of how many? No. Yes. Good. Very good. All right. And how am I going to draw this? C in the middle. Okay. C in the middle. And H is around. And what do we put between them to start? Single bond. And then we complete the octet for each surrounding. But hydrogen's an interesting case because what's a complete shell for hydrogen? Just 2. And this hydrogen already has? This hydrogen already has? This has? This has? Awesome. Carbon, let's count electrons. 2, 4, 6, 8. And how many do we need? Hey, we just made a structure. That's pretty easy, wasn't it? All these bonds we would call sigma bonds. Why?
Because it's the first bond.
Because it's the first bond between 2 atoms. We always call that a sigma. If it had a double bond, the second bond we would call pi. But we'd still call one of the 2 sigma, the other pi. Yeah. Something actually can't make 3 pi bonds. I know what you're saying, but something actually can't make 3 pi bonds because the most you can ever get is like you can only get triple bond to one other atom. So that'd be 2 pi bonds in a sigma. Or you could make 2 double bonds, like carbon can do that, right? But even then, I guess you'd get 3 pi bonds in a lesson that'll be coming up called expanded octets. But anyway, do you number them? More than that, we're going to talk about their quantum numbers. We're actually going to talk about, just like how we define the quantum numbers of an orbital of an atom before it bonds, what we're going to do today is look and say what happens to the orbitals once they've bonded. Because bonding in the covalent sense, in the ionic sense, there's nothing new to learn, right? So in an ionic bond where magnesium gives away its electrons, well, all you have to do to its quantum numbers is just say, well, those 2 electrons are gone, but nothing's changed, right? And then say chlorine took those electrons. Well, now chlorine, instead of being 3p5, it would be 3p6, right? Like it would just have 6 electrons there, but we didn't have to learn anything new, right? But with sharing, what's the quantum number of a shared electron? What's the quantum state of an electron that's being shared? And that's what we're going to talk about today. Did that answer your question by saying I'll answer your question later? All right. So what I want to look at is this. I want to look at the problem. So each hydrogen in this actually has the same electron configuration, right? Because they're all hydrogen. And so I want to talk about, before bonding, the electron configuration of the hydrogen. And it's very simple. What is a hydrogen atom's electron configuration? Yeah. It's got, and we're actually going to draw it. We're going to say 1s, and we're going to show that it's got 1 electron in it, right? Okay. What about carbon? 1s, 2, and then 2s, and it has 2 electrons, right? And then it has 2p, and how many electrons does it have there? 2. Okay. And I hope you can see the and that would go like that, of course. Pretty sure it would. I just wrote it that way. I'm a chemistry teacher. Let's move on. Oh, you don't trust me? You don't trust me. She doesn't trust me. And Kate's trying to correct me. Ruba doesn't trust me, and Kate's correcting me. And now Natalia's about to join in the abuse. I feel so attacked. Don't. Oh, what? Oh, sorry. Oh, it's too hard on Natalia to play along with Orlando's charade. Fine, yeah, how should this be, Natalia? Yeah, they go side by side. Whose rule is that? Hans rule. Okay, oh, my eraser isn't working. My plan is foiled. Okay, now, seriously, what is the problem here? Because if these are going to share electrons, we don't have 1 hydrogen. We actually have 4 of them, right? And I'm going to number them. We'll call this hydrogen 1, hydrogen 2, hydrogen 3, and hydrogen 4, right? Does that make sense? So that's hydrogen 1. And then let's put hydrogen 2 over here, and it's got 1 electron and it's 1 s orbital, right? And I'm running out of space, so I'm going to put hydrogen 3 up here, and it's got 1 electron and it's 1 s orbital. And we'll put hydrogen 4 down here, and it's got 1 electron and it's 1 s orbital, all right? And that's a little chaotic. Maybe to separate them a bit, I'm even going to like I'll put a box around each one. I don't know if that's more or less chaotic, but each of these represents an atom that has electrons, right? And we say when they go to make a covalent bond, what are they going to do with their electrons? They're going to share them. They're going to share them to accomplish what? Make sure that the shells end up being full and stable, right? Stable, and how do they get stable? By being full. Cool. So now, let's have that happen. And it doesn't really matter which one comes up first. Let's say hydrogen 3 comes along, and if they're going to share, yes, I want it right in that bin, right over there. Thank you. Hi, Ruby, how are you doing?
I'm good. How are you?
Good. I'm doing well, thanks. We just started this note, so hopefully. I'm going to make all these have negative spin, just so sharing will be easier, right? So we'll have one with positive spin, one with negative spin. Does that make sense? So no problem. When it comes time to share, H3 has this, I'll use a different color actually. Let's talk about this bond right here between carbon and H3, right? Okay, there's H3's electron that it's going to share, and there's carbon's electron that's going to share, and it shares these. And assuming now that these electrons spend time in both orbitals, does that work? This 2p would now have one with positive spin and one with negative spin, right? So does that work? Cool. Okay, great. Now let's say we have H4. Let's look at this bond. And that could be between this electron here and that electron there. Does that work? Yeah, right? Because this one has positive spin, that one has negative spin. And does this hydrogen now have a full shell there? Yeah, great. What's the problem? That's right. So now the problem is when these guys go to share, I guess they could share with each other, but that's not the structure. There isn't a bond between hydrogen and hydrogen, right? It tells us that the bond is between hydrogen and carbon. And more to the point, this structure, if you actually look at it, if you take some methane and you do X-ray crystallography with it, so you get it cold enough that you can get it into a solid crystal and shoot X-rays through it, that's how we figure out the bond angles and things like that. We do it with a physical method, where literally if you take something once it's crystallized and you blast X-rays through it, the bonds in these are so close enough that they cause X-rays to have interference patterns. Like when we shine light through a slit and we get weird patterns. And people much smarter than I am can interpret those lines to tell you the angles between things. And what they tell us is all 4 of these bonds are the same bond. Does that make sense? They're identical. All 4 of these bonds are identical, but that isn't possible based on their electron configuration. Does that make sense? So there's a problem, which is that research shows that all 4 CH bonds in CH4 are identical. But that doesn't fit with the electron configuration. I don't know why I'm writing this so small. This is the only thing that has to go in this space. I think I was thinking I was going to have to draw the next step in there, but I don't. So you can use your space to actually write that in a way that doesn't look ridiculous. I'll change mine later. Or you can leave a space and you could draw, I don't know, a cat. Draw me a cat, whatever. I didn't say sound like a cat. I said draw a cat. Good Lord, try to pay attention. So do we all see that problem there? That, like, it's not even that, because you could imagine a world where something weird happens, right? Like, maybe these hydrogens both share with this orbital, right? Like, that could possibly happen, right? Like, this hydrogen shares with that orbital, and this hydrogen shares with that orbital, and now that orbital is like whatever, right? Except that would be fundamentally different than these ones, right? That'd be a different thing happening, which means you'd expect to see it look different, right? You'd expect the shape to be different, or you'd expect the behavior to be different. But when we look at CH4, observationally, we see that all 4 bonds are the exact same. There's no difference between them. And that doesn't work with this electron configuration. So what must that mean? Well, it must mean that something happens. Does that make sense? Deep insight. Something happens. Lovely. Thank you, Kate Audette, for interrupting me mid-thought, but it's very nice. No, I said thank you, not apologize. I guess I said it sarcastically, but I actually didn't mean it sarcastically. No, I don't think I'm passive-aggressive. I think I'm aggressive. I don't think I'm passive-aggressive.
Okay.
Passive-aggressive implies somebody who is like not shouting at people and yelling all the time, right? Whereas I would say that I'm just mostly aggressive. Not in my personal life, but in my like teaching life. Anyway, so something must happen. Now, to be clear, does it look like anything has to happen to the hydrogens? Could they all behave the same way? Sure, right? Like they all have the exact same electron configuration. So something must happen to carbon's valence electrons to make all 4 bonding pairs identical. And the problem is, the reason they wouldn't be identical no matter what is that carbon's valence, hydrogen's valence is easy because it's a 1s orbital. Carbon's valence isn't in one kind of orbital. It's in 2 types of orbitals. There's an s orbital in its valence, and there is a p orbital. Those are different orbitals, and they have very different shapes, right? And the other thing is, and we don't have to talk about shape yet, so you don't have to draw this, but the other thing is we know that p orbitals are orthogonal to one another. Oh boy, what's that mean? Nope. They are all attached to each other, that's true, but that's not what the word orthogonal means. Come on, mathletes, go. Nobody? Nobody's an athlete? When you say things are orthogonal to each other, if you're only talking about 2 things, you could use the word perpendicular. 2 things that are perpendicular to each other are, they intersect, and specifically how? At a 90-degree angle. If we expand that to more than 2 things, and I'll let you decide how many things can be this way, when things are orthogonal, it means that a whole set of things are all perpendicular to each other thing in the set. Does that make sense? So if you look at the p orbitals, you have one p orbital that goes like up and down like this, but I'm just for simplicity going to draw it as a line. But you can imagine that's this one that has that barbell shape like that, right? And we call that on the y-axis, right? And then we have one that's at 90 degrees to it, right? And that's on the x-axis, right? But then we have a third axis, which goes back in space, and it is at, and I put that 90 degrees in a silly spot, because if I had just put it here, I wouldn't have to erase it. And then we have this third axis, which we typically call the z-axis or z-axis. Though actually we would usually call this y and that z, but it doesn't really matter. You pick your direction. And it is at 90 degrees to the y-axis, right? If you picture it's kind of moving away from you. And it's also at 90 degrees to the x-axis. Everything is at 90 degrees to everything else. That's an orthogonal set. Does that make sense? And if it were the p orbitals that were making the bond, then this is what CH4 would look like. That would be a carbon, and there'd be a hydrogen here, and a hydrogen there, and a hydrogen here, and a hydrogen there, and the angle between all the hydrogens would be what?
40.
Either 90 degrees or it would be at 180, right? And actually, even then, you get this weird set because we only have 4 hydrogens, so presumably one would go on the x-axis, one would go on the y-axis, and one would go on the z-axis, right? And so if you did that, you would end up with this weird thing, but maybe this hydrogen Does the hydrogen move across the atom? Like the electron could, but the hydrogen wouldn't be able to, right? Do you see that? Right? Like surely the electron, sure, it could orbit both sides, but then the hydrogen would be kind of stuck to one side. Does that make sense? And any way you draw it, you would have this thing where half the molecule, even though it has the electrons from the hydrogens aren't really there, right? And that's what the math would predict. If they stick on the p orbitals, that's what it's going to look like, right? And then one of them would have to double up, but only one of them. Or I guess it would double up with the s orbital, so it would be down here. Do you see what I'm saying? Like, no matter what you do, you don't get an even shape. Does that make sense? But when they studied it, what they actually found is that you've got carbon in the middle, and you've got 4 hydrogens, and they are perfectly evenly spaced out around it in 3 dimensions. And if we go like look on MolView and show you methane, show you CH4, you'll see that they are perfectly spaced out. But that doesn't make sense if you're working with p and s orbitals, because p and s orbitals are at 90 degrees to each other, right? And the problem with them is you don't end up with 4 spots to put something. With p orbitals, you end up with 1, 2, 3, 4, 5, 6 spots, right? And they're all at 90 degrees to each other. So if you take 2 of those off, so now you have 4 things. You have a few things that are at 90 degrees to each other, and then you're going to have some empty spots. So you'll also have some spots that are at 180 degrees to each other. Does that make sense? It's not even. When we look at CH4, and again, this is done experimentally, this is what we see. It's perfectly evenly spaced out. So that if you rotate this, if you shut your eyes, rotate it, and then open your eyes, you can't tell which hydrogen was which because they're perfectly evenly spaced out. Does that make sense? Like, okay, everyone, let's do it. See this hydrogen right here? All right, we're all talking about the same one kind of sticking up and to the right here. Shut your eyes, all of you. Don't cheat, shut your eyes. Okay. Okay, which one is it? Yeah, because you cheated. That's not helpful.
No, the bottom left.
Bottom left? You think it's bottom left? Who else thinks it's bottom left? Who thinks it's bottom right? Who thinks it's top right?
Excuse interruption.
Yeah.
I did Charlotte Lidke. Could she come to guidance?
Yeah. Charlotte, would you like to go to guidance?
I would not, actually.
Who thinks it's this one? Nobody? Nobody thinks it's this one. Nobody thinks it's that one. Not a single person thinks it's that one. But people think it's this one. This one? Can I tell you, I didn't pay attention. I have no idea. Because the point is, you can't know. I have no clue. I didn't even bother looking. I just wiggled it around some. Because you can't tell. Yeah.
If there was like another atom, like another atom near it, would you be able to predict, like...
That is such a good question. It's such a good question. And the answer is no, not amongst the hydrogens. You'd be able to predict, obviously you would know which one the other one was, but the 3 hydrogens would still be. So we would say that's a non-chiral molecule. And in fact, even if it was 2 and 2, you still couldn't predict its orientation for the hydrogens. But if all 4 were different, then obviously you'd be able to tell based on that. That's a concept called chirality. We'll talk about later. Perfect question. Just 3 days early, but a perfect question. So long story short, it can't be the p and the s orbitals. Doesn't work. It doesn't work with what we know this thing looks like. So if the facts don't fit your theory, you got to change the theory. Now, again, what we have for orbital notation works perfectly when atoms are on their own. All right. So if we make ionic gases, or if we make atomic gases out of things, in other words, if you get things hot enough that they form not just a gas, but even the things that normally would be diatomic don't have to be anymore, and we check out what's going on with their electrons, we see that fits perfectly our configuration here. So we know that this is true when carbon's by itself, and we know looking at this that it can't be what carbon's electrons look like once it makes a bond. So we need to explain that. And the answer is, when this mess up happens and the shakeup happens, these orbitals, the s and the p orbital, have to change. Does that make sense? They have to change. And they have to change so that instead of being 2 separate sets of orbitals, they become 1 set of orbitals. And when they do that, how many spots will they have? How many electrons will they be able to hold? The 2s used to be able to hold, and 2p could hold as many as 6. And when we put them together, they're going to be able to hold as many as 8. And so what we say in our theory happens is that these orbitals combine. And they combine so that we get a new orbital that's made up of the s orbitals and the p orbitals. And what the terminology we use for that is we call them hybrids, right? One of my cars is a hybrid. It has a gas engine, it has an electric engine, so we call it a hybrid. Makes sense? This is orbitals that are made of an s orbital and a p orbital, actually 3 of them, so we call it a hybrid. And specifically, since it's made of an s orbital and 3 p orbitals, we give it the very clever name of an sp3 hybrid orbital. It's a hybrid orbital that's made of an s orbital and a p orbital. Oh, how many of those? 3. Does that make sense? Good name. Often things in science have crappy names. I'm going to posit that this has a good name because it tells you exactly what it is. Does that make sense? So let's take a look. In this, there's a big thing going on here. It's just what we just talked about. What happens is this. Carbon in its unbonded state. No, don't be sorry. I'm sorry, I want to see the board, Orlando. In its unbonded state, carbon has a 1s orbital that's full, right? It has a 2s orbital that's full, and it has a 2p orbital that has 2 electrons in it. And then in its hybrid state, what we say happens is that carbon's 1s orbital is not going to be involved because it's in, what's the n value of the 1s orbital? It's the n value, 1, which tells us it's in the first shell. Is that carbon's valence shell? No, what's the n value of carbon's valence shell? Carbon. 2, that's right, yeah. Its outer shell is shell 2. So shell 1 is going to be left totally alone. But shell 2, these orbitals are going to combine, and they're going to combine to form what we call an sp3 hybrid orbital. Now, the number 3 might make you think that we get 3 real orbitals, but we don't get 3 real orbitals because this is made of an s orbital and how many p orbitals? 3, for a total of? No. An s orbital and 3 p orbitals. If Tim has 1 orbital, and if Simon has 1 orbital, and Paul has 3 orbitals, and they put their orbitals all together,
4.
How many orbitals do they have, crew? Yeah, 4. Good. Yeah, no, of course. Listen, guys, anytime I do something like that, I'm not trying to give you a hard time. I'm just trying to be funny. Okay, so please don't feel offended. Guys, can I ask a question? Am I like an ass? Because if I am, you can tell me. You can be like, hey, Orlando, it's too much. Stop. And I'll stop. I don't mean to be a jerk. So if I am, just, let me know. Anyway, okay. And then, how many electrons did it have in its valence shell? It had 4. Now, it used to be that S got filled before P because S was lower energy. Aufbau's principle says we fill lower energy orbitals before full ones. And then, in P orbital, the first 2 suborbitals, ml equals -1 and ml equals 0, both get 1 electron, because Hund's rule tells us that we put 1 in each before anyone gets a second. But now, these orbitals have been turned into just all the same, which means now the Aufbau principle tells us this is a single orbital. So it's going to get filled all together. But Hund's rule tells us that how is this going to get filled up? 1 at a time. How many electrons do we have to work with? 4. So now they're going to get filled in here. And now... don't worry about that. The spin, when all is said and done, every orbital is going to have one that's positive, one that's negative. We have no way of predicting whether it starts out with a positive one or a negative one. So I just arbitrarily pick one and go. That's not the important part. When all is said and done, it's important that if it has 2 electrons, they have opposite spin. It doesn't really matter which one is which. Did that answer your question? Good. So now, what do we notice about these? Well, now, each of these orbitals is ready to form a sigma bond. And not only that, but when these orbitals form a sigma bond, in other words, and when I say form a sigma bond, what do I mean? I mean that they are going to have 1 electron that they already started with, but what's going to take the second spot in that orbital? an electron that doesn't belong to carbon, but an electron that belongs in this case to hydrogen. Does that make sense? So the second electron in each of these is going to come from that carbon. But the neat thing is not only are these ready to form a sigma bond, but when they do it, all four of these orbitals are identical, right? Which means that we would expect all four of the bonds to be identical. And that matches the experimental data. Does that make sense? So hybridization theory, and when we say theory, what we mean is like, this doesn't actually tell us the order in which this happens. I can't sit here and tell you, so the first thing happens is that carbon hybridizes its orbital and changes shape, and then the hydrogen comes. But rather what we're saying is here is that like, when the bonding happens and when we end up with this new chemical, SCH4, we know that the bonds are all identical and the orbitals are all evenly spaced from each other. And we know that doesn't match normal p orbitals and s orbitals, so we have new orbitals. And the s and p orbitals, there's no evidence of them existing at all, right? Does that make sense? So what we say is that we've formed new orbitals. When they formed things like that, well, that would take different research to figure out. But this explains the observation that what we end up with is four bonds where all four bonds are exactly identical to each other, have the exact same amount of energy level as each other, and form the same shape, same dimension, and that shape is different from either an s orbital or a p orbital. So we say, well, what must have happened is the s orbital's gone, all three of the p orbitals are gone, but in its place we now have four new orbitals that have this different geometry and different energy levels. So we give them a name, and we say, well, this is a new hybrid orbital, and it's made from the electrons that were in the s orbital and all three of the p orbitals, so we call it an sp3 orbital. Does that track? Does that feel logical? You had a hand up. Huh, look at that.
I was gonna ask if they had like different shapes because it's 2 and 3, and if your shapes came from the S and P one, maybe the new set.
Yeah, so where the shape and what the shape of every orbital, we haven't talked about this yet, but in the end, the shape of every orbital, this was true about the ones we've already learned about, s, p, d, and f orbitals. The shape is basically electrons have negative charges, right? And so they are attracted to the nucleus, so they're pulled towards the nucleus, but they also have momentum, which means they want to keep moving, so that defines an orbit. And if you just had one electron, it could basically move in a perfect circle around the nucleus, and so we get a spherical orbital. We call that an S. As soon as you start introducing lots of electrons, they want to move around the nucleus, but they also want to stay away from each other. Because they're attracted to the nucleus, it's positive, but every other electron they are repelled by. So the shape of orbitals has everything to do with the fact that electrons try to get as far away from each other as possible. And if you're just dealing with one atom and say 6 electrons, then the best way to do that is that 90-degree orthogonal arrangement, which we call a p orbital. And that's why you get that shape. Whereas when you have 10 to deal with, that shape is no longer the most efficient way to keep them away from each other. So we get these new shape arrangements. And versus when you have, does that make sense? So that's why the S, the P, and the D, and the F orbitals have different shapes. Because when you have different numbers of electrons, there's different ways that it's best to keep them away from each other. And in this case, we actually only ever have 4 things to think about, right? Because we're making 4 bonds now. And so this shape, which we're going to talk about shape on Tuesday, but this shape is the ideal way to keep 4 bonds as far away from each other as possible. Did that answer your question? If it's about shape and things like that, I don't want to go down that rabbit hole, only because we have a whole lesson on it, and so I just want to hold off. Is it? Great, we're going to hold off. Yeah. Because it's saying this orbital is made from an s orbital, just one of them, so we don't bother writing the s, and then it's made from p orbitals, but we need to know how many, because, spoiler alert, later on, we're going to make hybrid orbitals where we don't use all 3 of the p shells. Sometimes you don't. Sometimes you make it from the s and only 2 of the p orbitals, in which case we'd call it sp2. And sometimes we make it just from an s and 1 of the p's, in which case we call it sp hybrids. Did that answer your question? All right. So the result then is, in each of these cases, the second electron that could come to each of these is going to come from a hydrogen, right? This is going to be H1's electron. This would be H2's electron. This would be like H3's electron. And this would be like H4's electron. But the important thing to understand is that this will get filled up. So you'll have a full octet. And in each case, all of the suborbitals, one of the electrons will be from carbon, and one of the other electrons will be from whatever it's bonding to. And that is the definition of a sigma bond. A sigma bond happens when you share electrons in one of these hybrid orbitals. Does that make sense? So the definition of a sigma bond is when an atom shares electrons in an sp, and we'll say hybrid orbital, and we'll mention that that could be sp3, sp2, or sp. I'm going to put sp question mark here because it could be sp3, sp2, sp, or even just an s. Because, for example, hydrogen doesn't actually have to make a hybrid orbital. Hydrogen's really the only thing that can do this, because for hydrogen, if it tried to make an sp orbital, it's in what shell? Shell 1. Is there a p orbital in shell 1? No. So it actually just it uses an s orbital, but that really only applies to hydrogen, but still worth mentioning. So a sigma bond is from a hybrid orbital. And do you see how we just looked at the electron configuration now of carbon when it is by itself versus the electron configuration of carbon when it is bonding with things? Does that make sense? Cool. Now, this happens to have been a Lewis structure where the carbon had no electrons that weren't shared, right? And that makes sense because if you look at carbon, how many bonds does it like to make? 4, and each bond is 2 electrons. So carbon doesn't typically have any electrons that it isn't sharing in its valence, right? What is something up here that usually does have some electrons that's not sharing? Sure. Oxygen, sulfur, nitrogen, chlorine, fluorine. Basically everything that wants to make 3 bonds is going to have a pair of electrons it doesn't share. Everything that only makes 2 bonds is going to have a couple pairs of electrons it doesn't share usually, right? And everything that only makes 1 bond is usually going to have 3 pairs of electrons it doesn't share, right? Well, let's talk about them. Let's look at water. Let's draw a Lewis structure of water. And even though we all know the structure of water, let's still follow the rules. What's the first thing we do when we want to draw a Lewis structure? Okay, good. So hydrogen, there's 2 of them, right? This is H2O. We're all comfortable with water being H2O? Tell me now.
Yes.
Oh, good. So 2 hydrogens give us how many electrons in its valence? Yeah, 1 each. Good. What about the oxygen? How many electrons in its valence? 6. Good. Okay. And does it have a charge? No. So the total is 8 electrons. Cool. All right. How do we draw a Lewis structure? Well, we put the more electronegative. Normally, we put the less electronegative thing in the middle. In this case, hydrogen would make more sense to go in the middle. The problem, of course, being there that hydrogen it just doesn't work. So this is a rare case where the more electronegative things in the middle, but given as it's only 3 things, we'll be okay, right? So we're going to put oxygen in the middle, we're going to put hydrogen there, and what do we do between them? We put bonds. Good, we put our sigma bonds. Then we fill out the octets surrounding, but hydrogen is already full, and hydrogen's already full. Then we count the electrons. Because if we have enough, we're done, right? 2, 4, how many do I need? 4 more. Yeah, 8. 8 total, 4 more. And so I should put them on like this, like that. Looks really good. No, okay. I should do that, like that.
No, they gotta get together.
They got to get together? Well, that's what I did the first time. God, make up your mind.
No. 2 together on the top.
They gotta be 2.
Oh, Orlando, you got to put them together. He puts them together. Oh, Orlando, you put them together wrong.
2 on either end.
2 pairs. Okay, good.
Buddy. 1 on the top.
Call me buddy, all right? No, thank you. Not interested. Yeah, okay. They go here. Typically, that's how we do it. Okay, there we go. Awesome. So now, let's look at the electron configuration of oxygen. Let's carry on. Let's look at Let's look at oxygen's electron configuration. So normally, what's the electron configuration of oxygen? I'm a terrible human being. What's oxygen's electron configuration? Just normally, not in this case. Talk to me. 1s, yeah, how many in 1s? Yeah, very good. And then 2s, 2, and then 2p. 1, 2, 3, right? And 1, 2, 3. Now, yep.
Why do you always go from bottom to top?
I don't know.
I wasn't sure if that was like a specific order.
You'll see it both ways. I don't know that there's some specific rule. I find it more intuitive to think of the things that are high energy being higher on the page, I guess. I think that'd be my answer. But you definitely see it done both ways. And I don't think that one is correct and one's incorrect. I think just sometimes it makes sense to work your way down. And sometimes, I think like if you didn't know how much space it's going to take, it makes sense to work your way down because then you don't end up with awkward empty spaces. In this case, I left a certain amount of space, so we'll make it work. Did that answer your question at all?
Yes.
Okay, now, on the face of it, does this look like we could get away with not hybridizing? Because could we not just make a bond here and a bond there? Okay. And so that seems reasonable, but there's one problem. If we did that, what would the shape of water be? Because again, these are p orbitals, and p orbitals are at what angle to each other? P orbitals are at 90 degrees, which means if the bonds happened here, then what water would look like is oxygen, hydrogen, hydrogen. It would be Ben. Be patient with me. Be patient. There's a method to my obnoxiousness. But let's look at water. Is it bent? And the answer is, yeah, but not that bent.
It's 107.5.
Sure. Let's find out. Ah, torsion. I don't care about the torsion. Stop. Okay, there we go. JMOL angle. Ah. By the way, this is just simulated, so that might not be perfect, but what is that angle pointedly not? It's not 90 degrees, which means that it can't be this structure. Right? It might work, but again, the math tells us water doesn't have a 90-degree angle. Therefore, the p orbitals don't bond, right? Which means that even though it could get away with this happening, that isn't what happens. Which means we still form hybrid orbitals. So oxygen will actually look like this. 1s will go there, and then we're still going to hybridize here. Does that make sense? And when we hybridize this, how many s orbitals do we have? S orbitals, not the electrons. One orbital. And how many p orbitals do we have? Yeah, so what do we call this? sp? How many s's? Okay, good. I won't bother writing a 1 because that's just usually, you don't say I have one cat. You just say that's my cat. But how many p orbitals do I have?
3.
Yeah, I have 3 cats because I'm lonely. So what do I put here? sp 3. And you're right. How many is that? 1, 2, 3, 4. And now we just use Hund's rule. And Hund's rule tells us how many electrons do we have total to work with here? 1, 2, 3, 4, 5, 6. How do they get filled in? 1, 2, 3, 4, 5, 6. Okay, now let's talk about our structure here. These electrons, where are they in oxygen's electron configuration? These 2 lone pairs here. Where are they in this? Yeah, that's a lone pair, and that's a lone pair. Where is this in this configuration? I don't know, let's say it's this one. What's going to go in there? Well, another electron, which is going to come from where? Where's that red electron that I've half drawn in here? Where's it coming from? Yeah, and from where? Yeah, from this hydrogen here. Does that make sense? That hydrogen's going to fill that orbital in there. In fact, we're going to draw the 2 hydrogens here so then we can show it. And then what about this here? Well, that's that bond there. Does that make sense? And see now how we've drawn a Lewis structure, and then we've also written the electron configuration. And whatever's in your drawing has to also be in here. Lewis structures show the valence, right? So are we going to see these 1s electrons in the Lewis structure? No, Lewis structures don't care about anything but the valence. If I wanted to, I could have just written square bracket helium over here, right? We don't care about anything before the valence. In fact, as we move on, that's what I'm going to do. You know, even with the energy level diagrams, I'm just going to put everything below this is just the noble gas beneath it. These are going to show up here. And we said this doesn't work, even though it looks like it works. 2 pairs of electrons through those, this doesn't work because, again, these electrons would go everywhere, and these electrons would be at 90 degrees to these, which would be at 90 degrees to each other. That's not what water looks like. We know it's not what water looks like, so this happens. These orbitals combine, and they make a hybrid orbital. We call them sp3. Why do we call them sp3? Because they're made from an s and how many p's? 3. So we call it sp3. What's the 2 telling? That's right, it's in the second shell. This is the principal quantum. Does that make sense? This is a new shell. And that is what's going on here. And again, now if we show this hydrogen, we'll call this one hydrogen 1. We'll call this one hydrogen 2. Hydrogen 1 might be down here. I'm going to put a box around this. This is carbon, right? Hydrogen 1, well, what's its configuration? 1s. And it's going to have a negative electron, and it's going to have kind of this filled in here, right? Because this is the sharing. Does that make sense? That's where the bond is happening. And then hydrogen 2, what's its configuration? 1s. How many electrons in there? And just to make it work, I'm going to make that one have negative spin because in the other one I made it have positive spin, right? And what's happening here? Well, these are being shared. Does that make sense? That is the electron configuration of everything involved, and I guess by convention, the other ones I put the box around it and then put like that. Right? So there we go. So this is the electron configuration that explains this Lewis diagram. Does that feel okay? And again, why doesn't hydrogen have to form hybrid orbitals? Because it can't, because its orbitals are in quantum level 1, first shell, and there is no p orbital in quantum level 1. Right? So hydrogen is the one thing that can't form hybrid orbitals because there's nothing to hybridize. There's nothing to share. There's nothing to combine with. How's that? I don't want to go too fast. This stuff's tricky. Confusing, a little weird. But you see, and again, this whole idea is just that if you say, okay, well, this should work, but then you go, but if we did this, we'd see this thing. But when we actually look at it, we see this other thing. We have to say, well, something must be happening. There is so much value. Science is so much a game of going, okay, I think this is what happens. This makes sense. Then you go out and you look and you go, oh, that doesn't work. And then just that phrase, well, something must be going on. There's got to be something else that happens, right? And then just say, well, okay, what might that be? What might that be? And this model explains what we see. So this is our current best explanation for what that something is. What happens is the orbitals combine. That description matches the experimentation. And then when we get to the math of it, we go, oh, and the math works too. So this is probably what happens. Now, the atom doesn't know it's doing this. It's not like, all right, well, now we're going to hybridize our s orbitals with our p orbitals, which will form sp3 hybrid orbitals, and we can put electrons in the way. That doesn't happen. Atoms don't think. The electrons just move to where they're in the lowest energy state. That's what the universe likes to do. But then when we look at it and observe it, we can describe it, and this way of describing it makes sense, at least a little bit. I hope it makes sense. And it matches the math that we can use to describe it, so we describe hybrid orbitals. Again, it's a mistake to anthropomorphize it. It's a mistake to think that the atoms sit there and go, all right, s orbital, you combine with these 3p orbitals. What's really happening is the electrons are going where they have to use the least energy, because that's what everything in nature does. It goes to where it has to use the least energy. That's why water falls downhill, not uphill. If we go somewhere and you see water rolling up a hill, let me know. I'd like to check it out. Likewise, the electrons just go to where they're most comfortable. But this description of calling it a hybrid orbital, that's a human construct of describing it in a way that hopefully makes it make a bit more sense. What we're really doing is just describing what electrons do. And electrons do what's easiest for them. And what they do is they spread out. And once you're trying to put two things together, the 90-degree spread of p orbitals, which works great when you're trying to deal with 6 electrons is no longer the most efficient way to do that, because now you're getting up to that full shell. And so now we need a new shape. And we call that an sp3 hybrid shape. How's that? Okay? All right, one more thing. No, I just said there's one more thing.
Well, yeah,
I wouldn't be saying that if it was the end of it, would I?
I meant after this one more thing.
I know. Kate, I'm very sorry. I'm a terrible human being. Okay, so just to draw it, again, and label things, we would say that this is a sigma bond, specifically between carbons sp3 and H's s orbitals, right? Oh, because I'm testing you to make sure you're paying attention. It's certainly not because I'm confused and don't know what's going on.
You did it on the last one.
Well, and you weren't paying attention, were you? You would have told me.
You didn't say anything.
Quiet, Kayla.
What? Oh, I didn't even realize we used.
Okay, and then what are these? These are lone pairs of electrons. And where are they found? They're in carbons, or oxygens, sp3 hybrid orbitals. Sigma bonds happen between hybrid orbitals. Lone pairs live in hybrid orbitals if that atom is otherwise bound. Sigma bonds live in hybrid orbitals. Lone electrons that aren't shared end up living in hybrid orbitals. They don't stay at 90 degrees and 180 degrees to each other because that isn't the best way for them to stay clear of the stuff it's bonded to. So if we have to make a new shape for the stuff it's bonded to, that's also going to make the electrons that aren't making bonds want to move into a new shape to get out of the way. Does that make sense? So it's not just the bonding electrons that go into a new orbital, so do the lone electrons. Because otherwise, their shape wouldn't make good sense. If these stayed at 90 degrees, even though these were at 104 degrees, then this one would be stuck really close between these two, and this one would have all kinds of empty space, which is how it looks in this drawing, because it's hard to draw things in 3 dimensions, right? But in reality, the lone pairs also spread out, so they're also getting out of the way. So it's not just sigma bonds that go in hybrid orbitals. As soon as this thing makes a bond, the sigma bonds will always be in hybrid orbitals, and the lone pairs will always be in hybrid orbitals. So what doesn't go in hybrid orbitals? Well, what's the thing we haven't talked about yet?
The first row, S1. What? I should have sure.
No, you didn't. I hope. If you did, let me know. I will get medical attention for you. Well, we've talked about lone pairs of electrons. Talked about sigma bonds. What haven't we talked about yet? Yeah, and in a double bond, one of the bonds is a sigma bond, so that's going to go in a hybrid orbital, but the other bond is a... So why do we give it a different name? Well, obviously we give it a different name because it's different. It behaves differently. And we don't call it a sigma bond because our definition of a sigma bond is a sigma bond happens between hybrid orbitals, which means a pi bond happens not between hybrid orbitals. Does that make sense? Sigma bonds go in hybrid orbitals. Pi bonds stay in the p orbital. All right, and that's what we're going to write here. So let's look at the nitrite ion, which we looked at already. So if you're okay with this, because I showed drawing it earlier, I'm just going to draw it. We said it was N with a double bond to one oxygen and a single bond to another oxygen, and it had to have that, and it has a lone pair of electrons, right? So we have a lone pair. Where will that be found? sp orbital, right? I'm going to put a question mark up there. And we have a sigma bond here. Where is that going to be found? In a hybrid orbital, right? That's true for both these sigmas. But this pi bond here is actually between p orbitals. And it could also be a d orbital, but we'll keep it simple for now. Why do we know this works? Well, again, it comes down to shape. The shape tells us this works, which is we find that the 90 degree of it is preserved when we have a pi bond. When you have a pi bond, all of a sudden now, one thing is at a different angle that still fits the old p orbitals. Everything else is at our new kind of more spread out angles, but one of the spokes angles changes to reflect the fact that we look and we say, oh, one of those p orbitals is still around. Does that make sense? So again, how do we know this? We did experiments. We got things into crystal structures and then we blasted X-rays and we looked and we said, oh, I can see the angles here. And when we run this, we get some hybrid angles, the new ones we find in bonding, but where there's this pi bond, we still also see vestiges of that electron orbital that is just straight through the nitrogen, that 90-degree angle, which tells us that we still have a pi bond. And so what that means is this. Let's look at the nitrogen and let's look at the oxygen. And specifically, I'm going to care about oxygen 1, because oxygen 1 is the one that is making a pi bond. Okay, ready? Nitrogen has a full 1s, right? And then, normally, I guess I'd draw it like this. Nitrogen would normally be 1s, 2 electrons. 2s, how many electrons? And then 2p, how many? 1, 2, 3, and it would have 1, 2, 3 electrons. What's going to happen is that these are going to make up the lone pair and the single bonds. Does that make sense? But this one is going to be for the pi bond. Does that make sense? So this will be used for the pi bond, which means it stays a p orbital. Whereas these will be the lone pairs and the sigma bonds, which means they form hybrids. Does that make sense? Okay, so let's do that. In the two, we first will have the hybrid orbitals. And what will they be? Well, they'll be an s orbital, and then how many p's? So what do we call it? 2sp, 2. And how many orbitals is that? 1, 2, 3. And then we'll also have a 2p orbital. And how many orbitals will that be? Well, we only kept one of them, so it goes there. And then now just look at what we said. What goes in the hybrid orbital? We have to have a lone pair. So that's going to look like this. And then we also are making 2 bonds. Well, if it's making a bond, how many electrons come from the nitrogen? Yeah, 1 in each, right? And then what's happening in the p orbital? Well, it's making a bond, so it's only going to have 1 electron. So this is what its configuration ends up looking like. And this will be where the pi bond happens. These will be sigma bonds. And that is a lone pair of electrons. How's that feel? If we go look at the diagram, it matches this. By the way, we can look at oxygen 1. Oxygen 1 has, how many lone pairs of electrons will these oxygens have? I should have drawn them. This one has 3 lone pairs. How many does this have? 2 lone pairs. So why did I draw that there? Okay, don't draw that. Oh, for gosh. Okay, I'm doing my best. It's the best I can do. I'm sorry it's not good enough for you. All right, so oxygen 1. First of all, oxygen always has a full 1s, and that's not in its valence, so it's not going to change. But now look at oxygen. And we can say, okay, how many lone pairs does it have? This one here. 2 lone pairs. How many sigma bonds? 1. And I should have actually... So for a total of how many hybrid orbitals do we need? 3 hybrids, right? And then it has how many pi bonds? Yeah, and that's going to be still a p orbital. Does that make sense? So in 2, we're going to get sp, but to make 3 hybrids, how many p orbitals do we have to use?
Oh, we used 2.
Yeah, we need 3 orbitals, right? And how many p's is that? Nope, because that would give us 4 orbitals, because we also have the s, right? So 2, which means what is left over? A p orbital, right? Does that match what we need? Yeah. What's going to go in these sp hybrids? Well, 2 of the things in the hybrid for oxygen are going to be lone pairs. And then you also get a sigma bond. Does that make sense? And then what about the p orbital? That's where you get a pi bond, so how many electrons go there? Good. And what that means is that this bond here, the pi bond, is between these guys. Does that make sense? And then one of the sigma bonds will be here. Of course, the other sigma bond in this would be being made to the other oxygen. Does that make sense? But this is the connection between N and O1. Do we see that? And then what are these? Lone pairs. Good. So these are lone pairs. That's a sigma bond. And that is a pi bond. All right. We'll finish off the last of this on Monday, but I bet you could finish it off yourself because you're smart. You're capable people. In fact, I challenge you to do so. We will take it up on Monday and try the homework. All right? Try it out. See what you can do. On your way out, my advice, come grab this. Lewis diagram practice. Won't hurt you. Have a wonderful weekend. Be kind to one another. Don't do anything Aruba wouldn't do. You heard me. Hi.